Alright, so let's begin again here. So, theorem linearity of Fouché derivatives. Basically, what I'm going to argue here is that if we have f and g differentiable at a point, then cf plus g is also differentiable, and this is the relation between the differentials. So, the core of the argument basically is that if we look at the eta, then eta of cf plus g, which would by definition be, this is what it is in principle. I argued before that was linear, of course, because it's the sum of linear transformations. Linear combination of linear transformations is once more a linear transformation. Anyway, so of course, by definition of, adding maps and scalar multiplication of maps, I can rewrite this as c times f of a plus h plus, there's c times f of a in here. There's a c times dfa of h in here. So bring those all together, factor out the c. Likewise, you got g of a plus h from there. You got a minus g of a from that, and you got a minus dga of h over there. So by definition of the eta, that's exactly eta of f of h, and that's exactly eta of g of h. So you see that the eta for the linear combination is the linear combination of the etas. And so this is, remember we argued that these were continuous at 0, and consequently we get that the limit, and more than that, the limit of the quotient of this with a norm of h is 0 by definition differentiability. That's just another way of stating differentiability at a point with this notation. So here it is. I'm missing, oh no, not missing anything, I just gotten trapped by my own notation. So this is equal to that, then I can break up the limits because both of these exist. So sum of limits rule, linearity of the limit really. And there it is. So that shows you that the differential is indeed, the differential of cf plus g is really that, satisfies the needed Fouché quotient, and there you go. So of course this reproduces many different linearity rules we know from before. The next theorem is a little bit deeper, but no less important, which is the chain rule for Fouché derivatives. If I have g from v1 to v2 and f from v2 to v3 differentiable, so I'm assuming that g is differentiable at a and f is differentiable at g of a, so the composite of f and g is differentiable at a, right? Then the chain rule for differential, then the composite is differentiable at a, and the differential of the composite is the composite of the differentials, assuming, it's the usual chain rule, the derivative of the outside function has to be evaluated at the inside, right? Well, this is what that looks like at the level of differentials. So df at g of a composed with dg of a. So there it is. Now, the proof I give here is not complete, but I offer the main points of it. The central point is just that if I, of course I got the eta. If g is differentiable, I have, eta of g is this. Differentiability of f at g of a, I have something like eta f of k is f of g of a plus k minus f of g of a minus df g of a of k, right? And then these differentials are linear transformations, so the composite of df of g of a and dga is likewise linear because the composite of linear transformations is linear. Then it just remains to show that the eta of the composite, with this being the alleged differential, in fact satisfies the needing limiting property. So towards that end, we consider the eta of the composite of f and g at h. So that's f composed of g at a plus h minus f of g of a. And then I'm using the alleged, this could, if I was wrong, this wouldn't actually, well, anyway. If I was wrong, then the limit of this is over to the norm of h as h goes to 0. It wouldn't be 0, but anyway, we'll see it is. Okay, so then the definition of composite. So this is f of g of a plus h minus f of g of a minus df g of a dga of a. So this is the definition of composite. And then the blue here, what I'm doing is I'm rewriting g of a plus h in terms of g of a, dg of a, and eta. right? Because you can solve. You may not notice this, but you can solve this, right? One of the things that you get from this is that g of a plus h is equal to, what's it equal to? G of a plus h is equal to g of a plus dg a of h plus eta sub g of h, you know? You can solve that for g of a plus h, and you can exchange g of a plus h for g of a, dg a of h, and this eta sub g of h. All right, which is nice because we have explicit limiting properties for these, all right? And so, with that in mind, I replace g of a plus h with its corresponding expression in terms of the eta and its differential and its fixed value at g of a, rather. And then, of course, I still have minus f of g of a and this differential. Then, my next move is to use the fact that I can expand g of a plus this being k. So I'm thinking of this whole thing right here as being my k, so to speak, in, you know, what I just had up here, right? So that gives me f of g of a, and so I do the same thing here. I solve this for f of g of a plus k for being a to f of k plus f of g of a plus df sub a g of a of k. And so that gives me these terms, right? Please, thank you, kids. And then, good kids, it's here, minus g f of g of a minus dfg of, I think he put Star Wars on his robot. What in the world? Okay, sorry, I'm distracted. All right, enough about robots. Going back to the proof here. So, of course, these cancel, you know, and these cancel, but we're, well, not, excuse me, this is function composition. I can't, not so fast there, you know. We're left with these terms. These cancel, but we're still left with the differential at g of a acting on this mess. Oh, excuse me, just acting on eta of g of h. And, oh, I'm an idiot. This, you know what? Sorry. All this talk of robots and such got me distracted. This actually, df g of h is linear, right? So this can cancel with that because this on that plus that is this of that plus this of that, right? So what's left is just this piece. The other two terms cancel there, and so we're just left with this and that. Now we'd like to show that as h goes to 0, the limit of this divided by norm h is 0. I think it's already clear that the limit of this goes to 0 as h goes to 0, which is, you know, I suppose necessary but not sufficient for the differentiability. You know, this is going to go to 0 because that's, you know, the linear transformation is continuous, and this goes to 0. So, you know, that's going to, all right, well, let me get to the actual arguments here. All right, so. First of all, we've got these two pieces, basically, right? This divided by norm h, I'm going to have this piece divided by norm h, and I'm going to have that piece divided by norm h. I'll talk about these separately. I will give an honest-to-goodness argument that shows 1 goes to 0 as you'd like. So, limit of h goes to 0 of that. This is a constant, it's a scalar. I can bring it inside this linear transformation, like so. Now, we can prove that linear transformation is continuous. And so it satisfies. So then I can bring the limit inside the continuous function, right, by the composite limit rule for continuous functions. And then, oh, well, that's 0 by differentiability of g. And so we have the differential of g of a acting on 0, which is 0. That suffices to show that this one piece goes to 0, right? On the flip side, this piece is a little bit more complicated. This guy over here, a little bit more troublesome. If I let k equal to that, then we have that eta sub k of norm k goes to 0 as 0. But unfortunately, I mean, well, that's clear because, I mean, if I call this thing k, I mean, certainly if h is going to 0, that's going to 0, because this goes to 0 and that goes to 0, right? So if I was to take this and divide by the norm of this, then, excuse me, if I was to take eta of k, where k is that, right? Sorry, my k got, formatting. So k, thinking of k is this, right? If h goes to 0, it's clear that k goes to 0. So, and then eta f of k divided by norm k goes to 0 by the given differentiability at g of a of f. But the hitch is, I don't need eta f of k divided by norm k going to 0. I need eta f of k divided by norm h going to 0, which is kind of a drag. So if I could find some relation which binds norm of h and norm of k, which seems plausible, given that this is how k and h are related, then if I had such a relation, then I could use this little squeeze argument. I could say 0 is less than norm of eta fk over mh, and now this goes to 0 by differentiability, and then by squeeze theorem that would go to 0, and if that goes to 0, I can factor out the m and still get that eta sub k, f of k over norm h goes to 0, and that would actually finish the proof. But I don't have quite a complete proof here. Now, in the posted notes, I do have a link to, there's like a link here to some notes where I found what appears to be a complete proof. And it is a little bit technical. I mean, like, the gap that I left here it's not an entirely small one. Anyway, there's the chain rule. Now, that brings us to the problem of partial derivatives of differential maps. I'm going to just stop. I think I'll stop the video right here, and I'll pick it up again. I got to go check on the kids. Sorry, guys.